Okay. The theme is an optimal online algorithm for finding all distinct subpalindromes of a string. I'll recall some definitions that a palindrome is a string that is equal to its reversal, and it is a well-known result that any string have n+1 subpalindromes. It is pretty easy to prove it, but I will not do it here. For example, here, you can see it. Okay. Our problem is can one find all distinct subpalindromes of a string in linear time and space? And this question was answered affirmatively, but with an offline algorithm. And the authors of in this paper, it was questioned: can one find an online algorithm to find all distinct subpalindromes of a string? And we will decide that we will find an optimal algorithm for this problem, and we will prove that this is optimal algorithm in comparison-based model. There will be lower bounds here. This is the main result as a theorem. Let sigma be a finite unordered or respectively ordered alphabet. Then there exists an online algorithm which finds all distinct subpalindromes of a string in O of n times sigma, or O of n log all n times log sigma time in n linear space. And this algorithm is optimal in comparison-based model. The main tool for our algorithm is the next lemma. The set of all distinct subpalindromes of a string coincides with the set of longest palindromic suffixes of all prefixes of a string. In other words, every subpalindrome of a string is the longest palindromic suffix of some prefix of this string. This lemma was proven in the following paper 2. But this is a simple lemma. For example, I show this is an example, the string AACBA, and the table where here is a prefix, and on the right-hand side is a corresponding longest palindromic suffix. And as you can see, AA, BC, AA is precisely the set of all subpalindromes for the string. So the algorithm to find all longest palindromic suffixes of all prefixes of a string is precisely the manager's algorithm. We found this. The previous authors did not prove it. This is a sketch, the pseudocode of manager's algorithm. We will not describe it here. I placed this pseudocode here to show that this is a short algorithm. It is well-known algorithm. This is online algorithm. We add one letter to the string, and we can find in a constant amortized time the longest palindromic suffix of the new string. The integer array red is a array of radii of subpalindromes of the string. Red I is equal to the radius of the odd palindrome center of the maximal odd subpalindrome centered in the place I and the position I. There is an even algorithm, manager's algorithm. This is an odd algorithm. Managers is precisely linear time algorithm. It don't depends on the size of alphabet. So it manages algorithm finds all subpalindromes of a string, but we have to verify whether the maximal suffix palindrome of a string has another occurrence than the string. We will use a version of suffix tree known as Ukanin's algorithm tree, Ukanin's tree. Okay. I recall what is a suffix tree. Suffix tree is a trie, which and in this trie we can read every suffix of the string. This is the example for string AACBA. This is a suffix tree. We can read AACBA, ACBA, CBA, BA, A. Ukanin's algorithm builds online the compressed suffix tree of a string. Compressed, it means that this edge, there is no vertices here, here, and here. This is one edge. This means compressed tree, compressed suffix tree. And Ukanin's algorithm builds online the compressed suffix tree, and one step of Ukanin's algorithm requires all log sigma amortized time in the case of ordered alphabet, or O of sigma in the case of unordered alphabet. The internal implementation of Ukanin's algorithm implements the parameter min unique suffix. Minimum unique suffix. It is the length of the minimum suffix of the processed string such that this suffix occurs in the string only once. This is the internal details of this algorithm. We can find it here, for example, in the source paper of Erkka Ukanin, or in some another book. I will not describe here internal details of this implementation of Ukanin's algorithm, but we can do it. And it is easy to see that using this parameter, we can verify whether the suffix of a string has another occurrence in this string. So our algorithm our algorithm to find all distinct subpalindromes of a string is to use manager's algorithm. And on every step, when we add append a letter to the string, we found a longest palindromic suffix of the string. And we have to verify whether or not this suffix have another occurrence in the string. So we read this parameter from the Ukanin's tree, and we have the length of the minimal suffix of the current string that occurs in the string only once. And if the new palindromic suffix is shorter than this parameter, then this is the new subpalindrome of a string. To prove the lower bounds, we reduce some kind of dictionary to our problem. Dictionary is, as usual, a data structure that contains some elements of the set, and it can implement basic operations like membership, deleting, or adding an element. But we will consider the special kind of dictionary, insert-only dictionary. This dictionary supports only one operation, insert in square. This in square x. This operation checks whether the element x is already in the dictionary. If no, it adds x to the dictionary. Only one operation. We will we will maintain such dictionary using our. Okay, just a minute. The next slide. It will be next. What is next? Now it is. We will prove the lower bound, reducing the problem of maintaining an insert-only dictionary to count and distant palindromes in string. Assume that we have a black box algorithm that processes an input string letter by letter and outputs after each step the number of distant subpalindromes in the string read so far. This is precisely the algorithm that we should design too, but in this here we try to prove the lower bounds for this algorithm. So suppose there is some algorithm, black box, and we will construct, we will construct an insert-only dictionary. Construction of dictionary. It relies on the second lemma. Suppose A and B are two different letters, so the following string has only one letter subpalindromes. So to implement in-square operation, we append consequently A, B, X to the string. And if our black box shows that the number of subpalindromes increases, then the added X by operation in square is a new X in this dictionary. And it is already here. Okay. This is a conclusion that our approach shows that it is hardly possible to design a linear time and space online algorithm for the discussed problem, even in stronger natural computation models than the comparison-based models, due to the reason that there is no fast dictionaries on these problems. No, there exists a more fast dictionary than the log sigma dictionaries, but there is no constant time dictionaries in linear space. Thank you. This is all.
Questions? So let me ask. Yes. As a get, we have an algorithm that can give us the minimal subpalindrome in the prefix of the string, right? And after adding
Given subpalindrome what?
the minimal subpalindrome of the string.
I didn't understand.
The minimal subpalindrome of the string. Yes? We
Yes.
had it, as you said, we had it.
It's one letter.
One letter?
Minimal is one letter.
One letter, it is a minimal.
Maximum one.
Yes, yes. Okay.
I thought it was.
I thought you are solving some real problems. No, I mean, I'm joking. So could you tell, I mean, is it your lemma about the low bound for dictionary?
Low bound for dictionary?
Is it
where?
something known or is it what you proved actually?
The first, simple information theoretic argument for this lemma, and it is proven. It is in comparison-based model.
So you mean you reduce sorting to that problem somehow? Or?
No, decision tree.
Okay.
Also the practical question, so there are several, this is actually an active field. There are several conferences on the stringology and there are experts in different places. Did you send to some, because probably here there are almost no real experts on this. Did you try to reach them?
Yes, we sent this with Arsenij Mikhailovich and, I forget to, this is Mikhail Rubinchik with me. He is not here. And Arsenij Mikhailovich, we sent this to the Prague Stringology conference.
And it is accepted.
Yes, it is already accepted.
Yeah, so you are in good shape.
If you have linear space, then you can load the whole string into the space, right?
Yes.
Then you can just, solve, just optimize time, not care about space at all. Is that correct?
Just time optimized. If we have no bound on the space, then in RAM model, of course, we have constant time dictionaries. No, if our alphabet consists of the numbers. And Ukanin's tree in this implementation have dictionaries, n dictionaries. So our algorithm have a time O(n) times log sigma. This log sigma is from Ukanin's algorithm, non-manager algorithm, manager's algorithm. So if you have more fast dictionaries, no, with the rate of the long space, you can implement constant time dictionaries. So you can have O from n, but you must implement several dictionaries. So I don't know. No, I think that in RAM model, no, I know that in RAM model there exists n times square root from log sigma divided by log sigma time algorithm. Because when we use log, I don't know.
Yeah, probably the question was just like if your algorithm uses just linear time, then it clearly uses linear space.
No, RAM model. I mean RAM model. In RAM model.
Yeah, okay, but the problem is not.
Sasha, I just meant that if you have linear space, then the online setting is where?
Yeah, okay. Yeah, okay, let's think, once again.